Hello, good morning. Welcome back to the Rust Planet. Today we are going to extend our talk on one of the that we have done, that is on Berkeley's packet filter and usage of IR library. So we have demonstrated how we can create a simple firewall using this technology and a library which is written in pure Rust. So after doing all these things, we have got one requirement from the teams that they wanted to monitor the CAN traffic. In this video, we have already talked about how we can monitor the network traffic. Now, in case we wanted to monitor CAN traffic, then how we can do that? Let's have a quick demo about that in today's video. So, if you guys are not aware of what is eBPF, I would highly recommend you to um, watch this talk first. This is a short video about what is eBPF and how we are going to, or introduction about the IA library, which is a Rust library, or we can in Rust we call them crates. So it's a Rust crate which is being written to encapsulate and provide a layer or to use eBPF in Rust programs, both in the kernel space as well as in the user space. So I would ask you guys to first have a look at this video. It's a short video, and then maybe we can start with today's talk. So in today's talk, what agenda or what points I'll be covering is we will be setting up a virtual CAN interface on our Linux machine. If you have any Linux machine, this can be easily done. Just give me a minute. Okay, I think the fonts are visible now. Yeah, so we'll be setting up a virtual CAN interface, and then we'll be capturing the data on that virtual CAN interface using our eBPF program. So I have already the code up and running because we have got we have already been working on this requirement for one of our internal clients, and so the code is already there. I'll just walk you through the code blocks, and I'll walk you through the steps of setting up a CAN interface on our a virtual CAN interface on our Linux machine as well. So the main focus or the main use case of this thing is to dump this thing on a Linux edge device on in the field, which will be having a actual CAN interface, and we will be monitoring the CAN traffic on that particular CAN interface. So let's first set up the CAN interface. So in order to set up CAN interface, I have already written a shell script. I'll just go through that, what is there in shell script. So I'll just nano it, or just we'll do cat can up.sh. So these are the commands which you will need to execute in order to set up the CAN. So we'll do it step by step. Mod probe vcan. Okay, okay. Then operation not set. This thing. We need sudo privileges for that. Mod probe. You know what? Let's do one thing. I'll just run this script directly since. So these are all the commands which you can follow. You need to insert the kernel program or kernel module into the kernel first. Then we need to link it so that it will be available on our ipconfig list interface, network interface list, and then we can set it some speed of that, and after that we can set it up. So I'll just do sudo dot backslash can up dot sh, and it will ask me my password. Okay, fine. This will make your CAN interface up and running, and I will show you how we can verify that. So this will take some time because this is what do you say, my office machine. Let it verify my password. Okay, now our CAN interface is up. We can see using ifconfig. So here is vcan 0, Currently received packet, transmit packets are all 000. So in order to send the CAN message, you can just do CAN send. You need to provide the CAN ID. Now, people who are familiar with CAN protocol, they already know CAN ID can be our A5D, A5D hash, and then CAN payload of, let me give you any payload, 56, 67, 78, 89, 99, 00. So these are how many bytes? 1, 2, 3, 4, 5, 6. Okay, so we got an error. So the actual this thing is we need to specify the interface also. We can 0. So this has sent the message on your we can 0 interface. Now we can check that as well. We'll just open a terminal. Let me ask you one more terminal over here. We'll do can dump. We'll run can dump utility over here. Over here, we on interface we can 0 and we'll run it continuously. Okay, so this is can dump is running. Now here, let us make them side by side. So I will just once again send the can send message. So you can see over here we have got our can message on virtual can, and the data length is 6. Our ID can ID is 25D. Okay. Now let's see how we can intercept this messages using our eBPF program. So let's go back here. This is our code already there. So I'll just open it in VS Code. Now, for those who already know what an eBPF program looks like in IA library or IA crate, this is just a repeat of the information. So I'll just quickly wrap it up. We have three folders for a normal IA program. We have a eBPF folder, we have a common folder, and we have our user space folder. So eBPF folder will consist of our kernel space code, which will be hooking onto a particular function or a particular interface or particular system call or anything like an eBPF program does. This code is responsible to hook onto a particular entity which we have specified, and it will get the data packets from that particular source, and it will send those information to the user space code via using hash maps. Now those hash maps, which hash maps we have to use depends on our use case. So currently I have used perf event arrays because those are quick to implement and easy to implement as well. But they do have some performance costs. So we'll dive deep into that in our upcoming videos. Then we have a common folder which will consist of a data structures which are going to be used by your user space and your kernel space code both. That's why the name common. So can monitor common. This was about can monitor common, and then finally our user space code. So this is the user space code which tells you that or which tells kernel that this is the compiled kernel space code. You have to insert it at this particular watch point or system calls or anything or particular interface in this case, and then it will collect the data from that particular kernel space code, and then you have to decide what you wanted to do with that data. So for example, in my case, I'm just pushing that data to a particular file, and on that file my server is running, and that server is pushing that data to AWS and Azure Cloud respectively. Now, let's try to understand the eBPF code first. We'll go to, it is a very simple eBPF code. You can just, what we can say, you can just create this using IA utility. I will try to open that for you. IA, let's open IA website. And in this you can go to development environment. Finally, this is the Um, this is the command which you need in order to generate your first or any IA program. So if I want to just give you an information or just give you a demo, so we have executed a command cargo generate from this particular template. Here you can give project name. I wanted to do can monitor, so that is already there. We can do, for example monitor. Now it will ask you the type of eBPF program which you want to use. Now this type of eBPF program depends on the entity which you choose to monitor. For example, here in my case, I am using XDP. XDP is nothing but a program which helps us to, or which hooks onto a particular interface. Now, interfaces are nothing but this interface which we have already seen. If I just do if config, so these are the available interfaces for my machine. For example, ENP0S3 or VCAN 0. So these are the available interfaces. Now, XDP will just go on to this particular interface and receive or read the packets from that particular interface, whatever packets are going or either receiving. So this kind that is the type of, or that is the use case of an XDP program. There are multiple other things also we can do. For example, we can use trace points also in order to monitor system calls. What this trace points will do, it will go on and hook itself to a particular system call. For example, in this case we can monitor a system call which we need to check which system call is being triggered when a can message is being received, and then once we know that system call, we can use a trace point to monitor that system calls. So currently as of now, and there are multiple other k probes and return probes and LSMs and also there, we'll discuss about them in more detail. That is not a part of today's agenda. So on an average, just looking at the overview, I will just go with the XDP program, and it has created my XDP program. So I can just go cd example monitor and open a code window over here. So as you can see, this is my eBPF code. It is very similar to existing to my actual can code which is running. So I will just, what I have done is try can monitor. So once we get the XDP context from the XDP program, it depends on us how we want to extract the data from that particular context. So in this the IA tool which gives you the generated template, it just gives you the XDP context. What you wanted to do inside that depends on you, how you are going to extract the data from your XDP context. So what I have done from XDP context, I know I want to extract can frame. So what is the first of all, I have to create a can um, data structures. So for that data structure, I have created a can data struct on my common library, that is here. So for as far as my knowledge is there, so in a particular can frame, I have done some googling and all, and found out that can frame consists of a can ID, can data length count. It has some padding bits, it has some reserved bits, and finally there is a can data. So this is a flex can frame data, which has a 32-bit can ID and 8 bits of data. In one frame, there can be 8 bits of can data. Okay. Now this data structure or this struct I have created in our common folder, and that particular thing is being imported here. Can monitor common and can frame. Now the very straightforward thing is we can directly get a pointer of context and dereference that particular pointer into a can frame struct. Doing that, after doing that, we can extract a U32 value. That is, first U32 value would be can ID, then second U8 value will be can data length count, and finally the data remaining that can also be extracted from this particular pointer. So in this way, it is very simple thing, just typecasting a particular pointer and getting the values from that particular location into our struct. So I have got ID, I have got data length count, and I have also got data. So this is enough for me. Now what I have done, I have created a local can frame so that I can send this data to a particular performance event array. This is nothing but a hash map. This will help me to send this data to the user space code. So this is again perf event array is again available in our IA library. You can directly import it, maps and perf event array. Um, Mostly it is not being given to you in this particular IA tool. So they will give very minimum things which are required to write. You need to import it according to your usage. So as I mentioned, usage of hash maps is directly depends on your use case. So I have used perf event array because it is very straightforward and easy to implement. So just declare an array. It is a hash map with maximum entry of 1024 currently. And these can events, I am just outputting the local can frame with context, and flag is 0. Uh, I'm not sure about significance of the flag, but I've always kept them 0 until now. So this particular line of code will put my local can frame onto my hash map, which will be accessible to my user space code. And that's all. That is done. We can add some print statements in the kernel space also, like using this info macro. Received packet ID with ID this, received packet with data length count this, and received packet with data this. But let's comment this out because we have already sent the data to the user space. We are printing the data in user space. So this program will attach itself at this particular XDP. So this is again an XDP macro which will expand itself into, if you go inside it. So this is a proc macro. It will expand and it will attach this particular can monitor program at that particular can instance. Okay, now we have seen eBPF code and common code. Let's have a quick look at user space code. So user space code is also not very difficult, or I would say it is pretty straightforward. We are setting up logger environment. We are checking the hash map capabilities, and according to that, like the hash map which we have created, it has to be checked whether the kernel has the capacity of creating that hash map, because there are various flavors of Linux which are designed for Linux like user resource constrained environment, for example edge device and all, and this particular project has is meant to be run on edge device. So what we are doing here is we are just checking what is the limit currently, and if the limit is already existed exceeded, then we will return an error that simply this hash map cannot be created, or that perf event array cannot be created. After that we will create the instance of a BPF program. Again, this is the template which is generated by Aya. So this all things you will get it generated in your template also. For example, this is the template which we have created. So if you go into user space code, you see everything you get here created. You just need to change your name of your kernel space code. Okay. So what I've done here, my kernel space code name is can monitor, and then if you have created the XDP program, then you have to attach it at particular interface. So here I have attached it at vcan 0. So program it is attached at vcan 0 interface, and if it fails, if there is no vcan 0, and then it will just panic and it will give you this error that there is no vcan 0 interface. Okay, this particular argument you can specify from the user also. Currently my Linux system have only one virtual can 0, so I have just hard coded it. Then I think this makes sense until now. Okay, I cannot verify it. If not, if there is any question, you can comment in the chat section, or in the comment section, and then we will have a look at it. Then I have created some in some data over here in order to, this is again user specific data. I wanted to send it using my unique ID. but we can ignore that. Then let's concentrate on this particular for loop. In this particular for loop, we are trying to send the data, whatever we have received, to first of all, we are printing the data locally. So here we are printing it. I want UUID, event ID, can payload. This is all my client specific data. I can, this again, what our interest lies over here is ID and data. So here I have extracted the can data from that perf event array which we have got. Again, in order to extract it, we are using the same thing. Let me show you how. So here we have got events. Now this event is nothing but an perf event instance of an perf event array, or an instance of an hash map. Now here we are actually reading the events from that buffer. Once we get an event, we are trying to again dereference them. We got a pointer and typecast it into can frame. Once we get the data, then directly we need to use this from function, can id from data, DLC from data. Actually DLC I'm not using it currently. Let's comment that out, thing out, unnecessary code. Data can frame from data and not data. Okay, in this way we can extract our values from that particular hash map, and then it completely depends on you what you want to do with that data. So what I'm doing, I'm printing it over here, and then I'm printing it in a particular file. And there are some further use cases for me lined up that will take the data from this particular file and do whatever next steps they wanted to do. For example, sending the data to some cloud instance and doing some analysis over there. Okay. Now let's try to run this code. I'll just open a terminal just to, I hope this thing is already built. But in order to build a simple IA program, I'll show you the commands. So commands are very simple: cargo, xtask, build hyphen eBPF. This will compile your kernel space code. Okay. Then our next command is cargo build. This will compile your user space code and the common part also. Then again we do clear clear, and now I'll just increase this thing. Okay. I'll run this code with, let's not do this thing because we are using print statement, so enforced is not required. So I'll just do cargo xtask run. It will ask me for sudo privileges because it is monitoring an interface. So it will definitely ask you for your root password. I have provided that, and then let it take some time. Till then we set up our can monitor over here. We'll set up our can send utility. So this is one utility where from which we are going to send a can message. Let me send can send v can 0. Can ID is AFD hash 223344556677 and 88. This is our can send. Here, okay. Uh, I hope this is clearly visible. We will do can dump. It will dump all the messages on vcan 0. Now here we are going to send one more can message of same data. So see, here we have got, we have intercepted the can data successfully in the required format. We have got our UUID, event ID, timestamp at which time we have got ID is AFD and data is this data. Correct? Now what we'll do, we'll generate a series of data continuously. So see here, the can data is being sent, and here can dump monitors that data. But our program is also able to capture that data, and in this way we are able to observe the can data on our Linux device or our edge device in on real time. And this can data is very useful for multiple purposes. For example, it can be used for your security monitoring purpose, observability frameworks, various use cases you can create. You can simulate, or you can detect whether your can is healthy, or can bus is healthy or not. Is there is some DOS attack is happening on can bus? Various use cases are there. You can detect if there is if someone is trying to do some malicious activity on your can bus, and those are the type of use cases which you can design, or that this thing, this solution will serve the purpose. Okay, so for today's thing, I think that was the agenda for today's talk, to demonstrate if we can monitor the can traffic using eBPF program, and that too XDP program. The next topic which I would like you guys to try, if you are really interested, is you can try this thing on your BeagleBone Blackboard, or any board which has actual CAN interface. For example, CAN 1 and CAN 0, CAN 1. And you can try to monitor the CAN data from that particular CAN bus or CAN interface. And then let me know in the comment section, like, are you able to monitor the CAN data using XDP program, or there is something else we need to try in order to get the data from actual CAN interfaces. So I will leave that up to you. Do let me know. Um, and that's all for from me for today's talk. Okay, if there are any other doubts regarding eBPF Rust implementation, comment in the chat section or in the comment section, and let us know your interest. Or if you want to try something new things out, then that also you let us know. We will collaborate and work together to make this thing happen. Okay, so for now it's all I'm done from my side. Uh, so that's all. See you next time. Enjoy your weekend. Bye bye.